So as we began talking about the hierarchical linear models last time, which is the final part of this class, and I know that unlike the linear model, it's getting more complicated, and you will mostly rely on the R package for your computation. So I think it's mostly important to understand what it actually means, what the model actually means, and how do you interpret when you should use the model, right? When should you want to use it, and how to interpret the R function output. So let's still use this model, random intercept model, to introduce the hierarchical linear model and linear mixed model. So we can write the same model in two ways. And the setting is that we have group data. We can also say cluster data. And this is very typical in settings when you, for example, education, when you have students from different schools, then you don't think the students are all exchangeable with each other, right? The school structure makes a difference. Or if you have patients from different hospitals, you want to keep the hospital as a group, as groups. So then this is the setting. You indicate or you index your group I from 1 to m. Then within group I, you have observation, or you can consider to be individual, j from 1 to ni. So if we write it in a hierarchical linear model, the first way to write it, hierarchical linear model, we basically index Yij as the response of the jth observation in group I. And we want to associate it with some covariate Xij. So for example, Yij may be the jth student in group I, and there's a covariate as the students, how many hours the students studied, right, for the exam. And Yij is the student's performance in the exam. So if I want to see whether studying longer can help the student get better performance. If that's the setting, then we have Yij regress on Xij. Okay, so what I give you just one example, but in general, the covariates could be more than one variable, and we just code that as a vector. So Xij, we say it's a p-dimensional vector with p covariates. And we're interested in their effect on Yij. So we have this common effect coefficient beta 1 to beta p, to indicate the effect of Xij on Yij. So we know that there's an intercept. The intercept here is tricky. We say it's random intercept model because we want the intercept to be specific to group. That means in each group, it has its own baseline. Some students, maybe in some schools, generally have better performance, even though they don't study. Maybe they have better background or better training previously. So therefore, this baseline intercept indicates when we don't have the effect of Xij, what is the baseline in group I? And of course, we always have the random error term, Xij. Okay, so here, what we wrote in this layer is within group I. We have this model within group I. And here, J goes from 1 to ni. Okay. And as we said, it's hierarchical. We have a second layer that is between groups. So between groups. That is how we model the intercepts. So right now we have n groups, so we have n intercepts, beta 0, 1 to beta 0, n. And there are n intercepts as n parameters. Like we said previously, sometimes we may have very small number of people, like n9 may be small for one group I. Therefore, having too many parameters may not be good. We cannot afford so many parameters. If we just have 2 people in this group, then you are using these 2 people to estimate the intercept, which is not ideal. Therefore, to reduce the number of parameters and to allow us to borrow information across the groups, we assume that these beta 0i follow a distribution with mean beta 0 and the error term indicated by delta I. Okay, and in this layer, I goes from 1 to n. So far, I haven't really written down the distribution of epsilon ij and delta I here. But basically, I'm assuming in this 2-layer model, epsilon ij and delta I are random. Okay, and beta and beta 0 are fixed. So how do we interpret this between group layer? We consider beta 0 to be the common intercept for n groups. And from this common intercept, each group has a deviation, delta I. And these delta i's are assumed to be random. So a common assumption, commonly, we like Gaussian assumption for random errors that have mean 0, right? So we assume that epsilon ij, they are IID within group I to be normally distributed, 0 mean, and we can assume that the error terms in each group I to have a different variance. So the variance can be group specific, sigma I squared. But still, they're all independent. This sigma I squared, instead of saying it's all equal to sigma squared, just allows some group to have bigger error terms, some groups have smaller error terms. But you are introducing more error terms, right? You have n error terms here. You may not want that. So, or you can just say epsilon ij, iid are just sigma squared, follow the same error term. And for the delta I, they are commonly assumed to follow a normal distribution with 0 mean and variance omega squared. Okay, so now if you put things together, you would have, let me see, one more thing is to assume that epsilon ij and delta I, they are independent. I don't know why it's, yes.
So why is it important that the epsilon are independent?
That's how we can decompose the variance. Otherwise, it will become more complicated. You can do that, but it's not necessary because every model builds on some assumptions and beliefs. Assumptions are beliefs, right? So we believe that the error terms are just due to some measurement errors we don't capture. So when you write down this model, essentially you believe that, oh, with those covariates, say education or working time, I can perfectly predict my exam output. But you cannot. The reason is that there are something we don't measure, and we throw those effects into the random error here. But these effects are different from the between group differences. The between group differences are just simply some schools have better education in general than other schools. And we just want to use the delta I to make sure that when we estimate those beta 0i parameters, they don't vary so freely. because we just don't have enough data to allow that level of degrees of freedom. So it's like this delta I, even though we introduce it here, but we don't think it's a random error. It's just a deviation of those schools from the common baseline. That's it.
You think that delta is a real signal, not school?
Exactly.
School
It's like a random measurement error. Yes. Yeah. 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 Okay. All right. Okay. Thank you for the question. Then this is the hierarchical linear model. Okay. So basically, if we wrap it up, we can say, so the other way, let's just say conversely, if we write from the bottom to top to bottom, the other direction, we can have beta 0i, IID following normal distribution with beta 0 as the mean, omega squared as the variance. Okay, and then Yij given beta 0i, RIID from normal distribution, the mean is beta 0i plus Xij transpose beta, and the variance is sigma I squared. And this sigma I squared can be reduced to a common sigma squared. So we have two-layer Gaussian distribution. Okay, this is the hierarchical linear model interpretation. Do we have questions? All right, if not, then let's talk about the second formulation, linear mixed model. Some people also call it linear mixed effect model. So let's put this short name HLM here. And this is LMM. The interesting thing is that they have a one-to-one correspondence with each other. So you can think of the linear mixed model as just, how to say it, as just we write the two layers into one layer. It's a one-layer representation of the two-layer hierarchical linear model. So we just directly write Yij as equal to beta 0, the common intercept, plus Xij transpose beta. So they all carried on, they are all carried down from up here, beta 0, Xij. So I basically put this beta 0i equals beta 0 plus delta ij. I just put this into the top one to combine them into one layer. So I have beta 0 plus Xij transpose beta plus delta I plus epsilon ij. Okay, so when I write it this way, I can clearly see that I have the fixed part here. No, nothing is random here. And I have the random terms here. Okay, it's a separation of the so-called fixed effect and random effect. Okay. So, you know, we have written the linear algebra or matrix form for representing linear models before. Now let's do it for this one. So right now I'm writing out each observation. This is the one observation representation. But now if I do the stacking, if I stack J from 1 to Ni, then I can have a group I linear mixed model in the matrix form. So I can just write Yi as Yi1 to Yin. Okay, I have Ni observations in group I. And I can have Xi as the so-called design matrix. First row, first column as ones. Then I can put Xi1 transpose to Xi transpose. Okay, the reason I do it this way is because in the previous line, I didn't include the intercept into the design matrix. Now I want to include the intercept in design matrix. So you will have one additional column here. If you say you have p-dimensional covariance, now your design matrix will have p+1 columns. You just have to be self-consistent. Okay, and then what I can do is epsilon. Okay, epsilon I stack everything to a vector. I have epsilon I1 to epsilon I ni. All right, with this, then you can see that the matrix form will be of the linear model would be y equals yi equals xi, and the vector is beta 0, beta. Okay, I stack them. The first one is beta 0. The remaining entries are from beta. And I need to have this delta I in the matrix form, but delta I itself is a scalar. So looking at the dimensions here, yi is ni by 1, xi is ni by, let's just write p+1. And this is one-dimensional, this is p-dimensional. So it's a p by p plus 1 by 1 vector. So here, to match the dimension, that's what I have for term, plus finally epsilon I. So this is the matrix form for the linear mixed model. Okay, so essentially, I still have the fixed effect in this xi term, and I think I have the last two terms to represent the random effect. Okay, maybe Junko, we can help close the door. It's a little noisy outside. So this way, we can show that something I can show you is that this model introduces dependency among Yij and Yik for being in group I. So I can introduce within group dependency in this model, which is something we don't have for linear model, right? For linear model, we don't have this random effect term. We just have the fixed effect plus random error. But now with this random effect term, we can have something interesting. Let's just do a calculation of the covariance between Yij and Yk. Okay, Yij, Yik. Let's look at their formulation again. So the fixed part doesn't influence their covariance, only the random part. Okay, so one has J, one has K, but they share the common delta I. So this is essentially the covariance of delta I plus epsilon Ij and delta I plus epsilon Ik. Okay, and now you can see the assumptions will help us. So right now, what we have is delta Ij independent of epsilon Ij independent of epsilon Ik. We also have delta I independent of epsilon Ij and delta I independent of epsilon Ik. So with all these independencies, I can reduce this covariance just as the variance of delta I, because the delta I is involved in both terms. And this variance of delta I, based on what we have right here, is omega squared. So therefore, you see that for two observations in the same group, they are dependent. Their covariance is omega squared. This is introduced by having the same random intercept. Okay, but if you look at two observations from different groups, if you check covariance of Yij and Y, say I prime K. So I and I prime are not the same group. Okay, then you can easily see that this covariance is 0. Okay, the reason is that you would have delta I plus epsilon ij, and this one becomes delta I prime plus epsilon I prime K. Then everything will become independent of each other. So we don't have the within between group dependencies among observations. Yes.
Is it generally true that like covariance A plus B, A plus C is equal to zero?
No. Oh, I see. No, you need to have independence between A and B, A and C, and B and C. You need to have those. Because in general, if you expand it, let's just say this. If you have that, then when you expand this covariance, you need to have 4 terms. XZ plus covariance XR plus covariance, how to say, YZ plus covariance YR. You need to have 4 terms. Yeah, and some terms are 0 because of independence. Yeah, I think it's the best way to understand this, go back to the definition of covariance as the expectation of 2 products. Yeah. So basically, this expansion is due to the expansion in the product rule. Okay, something I want to ask you, since you're talking about the dependence, I think many people may have this confusion about what is the dependent, what is independent. I remember I might have talked about this some while ago. But independence essentially means that knowing the value of one doesn't help you know anything about the value of the other. That's the most basic meaning, intuition behind dependence. But actually, if you think about linear model, okay, so this is something I just want to do a little deviation from what we're talking about now. Let's think about this linear model. Okay, if I just have Yij as beta 0 plus Xij beta plus epsilon ij. Okay, now I'm dropping this random effect. So with this model, if you have epsilon ij or IID from this normal mean. So what it means is that whatever value one error term takes doesn't tell you anything about what values other error terms take, right? Then if we write it in the mathematical term, Yij, Yij prime, okay? It should be 0, no problem. But how can you explain this fact? That is, what if Xij equals Xij prime? I'm just giving you the exactly same covariate for the 2 observations. Then these 2 covariates will be equal to the same mean with just differences in epsilon. So basically with this, then I can say Yij is the same thing plus epsilon ij, while Yij prime is equal to the same thing plus epsilon ij prime. But what this will actually happen in your data is that if the 2 responses share the same mean, share the same covariance, when one is bigger, the other is also bigger because this part is the same for them. Then can we say they're really independent? That is something I think is fundamental to when we say independence. Okay, so independence in this case, what it actually tells us is this thing. So when we have just Xij as a scalar, let me just put it in a simpler form. So what we're trying to fit is such a linear relationship, which means that when Xij is bigger, Yij is bigger. When xij is smaller, yij is smaller. But the error terms we're assuming are something like this. So it's actually what is off the line. Then basically, when we're saying Yij and Yij prime are independent, when we assume Xij being fixed, we're just saying, okay, around this point, what value they take, whether it's above the value or below the line value, they are independent. So one value could be above, one other value could be below, but they are both around this value. So in other words, this line showing that, okay, when the responses share similar Xij, then their response values should be similar. But this is accounted by the mean relationship, or the line we call this mean function, not by randomness. And randomness are just the errors around the line, vertically around the line, and we assume them to be independent. So it's just one perspective. So therefore, in the fixed design, it's easier to say, okay, covariance Yij prime are 0, because we consider this part to be fixed. But if we are talking about joint model, where the Xij can also change their value, it's no longer the case. Okay, in the joint model, then Yij and Yij prime not on fixed, not conditional fixed Xij, but we let Xij to vary themselves as well. Then Yij and Yij prime would have covariance, positive covariance. I hope this makes sense. So it's always like a variance decomposition perspective. What do you assume as fixed? What you assume as random? So in our perspective, we just assume that for different observations, their xj values are taken as fixed. We don't model their distribution anymore. Okay. So another way to think about this independence versus dependent is that if we have two Gaussian distributions like here and here. So what we can say, okay, if I have this random variable x, random variable y, if they follow this, a mixture of these two Gaussian distributions. So if you look at the observations drawn from these two, this joint distribution together, you would have a positive correlation, right? But if you are talking about conditional on the two mean values, you don't have dependence. Things become independent. So that's why this is something related to the so-called Simpson's paradox. You can check it. That means when we talk about correlation, when we talk about dependence, it can be different if we are conditional or unconditional. Okay, so all our discussion are conditional Xij. So treating Xij as fixed covariance is equivalent to say we think Xij as conditional. Okay, so this is just like a deviation from our major thing. All right, so let me see. Something people can use it to say about, let me see. All right, so we have linear mixed model and HLM, hierarchical linear model specified. And so now we can do a further stacking. So let's just try to generalize the model we already have for the random effect model. So recall that, just go back to last page. We write it in this form, yi times xi times time x equal yi equals xi times coefficient fixed plus some other thing times the random effect plus error, right? So for this one, because it's just random intercept, we just have a columns of ones. But if we also want to allow for random slope, then we may put some covariance here, okay? Then these covariance put here, their slopes will be random instead of fixed. So therefore, a more general form of LMM can be written as yi, still for group I. yi equals xi beta plus zi delta I plus epsilon I. Okay, so I'm just expanding that column of ones to this zi design matrix. So these are what we call random effect covariates. Okay, so in this case, if I make the notations more specific, I can say yi is ni by 1, n observations, xi ni by p, beta p by 1, zi ni by r, delta I r by 1, r random effects, epsilon I ni by 1. Okay, now furthermore, since I have n groups, right? I goes from 1 to n. I can further do a stacking to stack everything together across the n groups. Then what I can do is that I can do, let's say, stack the groups. What I can do is I can have y for y1 to yn as one long vector. So this like n1 from group 1 and n from group n. And when I do the stacking, the xi, they share the same p covariates, right? The covariates are shared. So I can stack them by row. So x, I can
So that one's one, every group has the same.
covariates, p covariates, because the p covariates are what you consider to have fixed effects. And these fixed effects are not group specific. Like education level, and their effects are the important things that their effects are not group specific. They are the common effects you want to learn about. Because like, for example, I want to know in general, how much can studying longer help me getting better grades?
And then are random effect covariates.
Are random effect, and they are group specific, right? Just like the random intercept, every group has its own intercept. So just consider this to be like the things you want to be group specific so that you can allow the groups to be different. You are not forcing the groups to follow just one mean function plus random error. Does that make sense? Yeah. And because, in the most, remember the model A, model B, model C we talked about last time. So in the extreme scenario, you just estimate each delta I differently for each group. In that case, you are fitting one linear model per group. Then the information or observations from the other groups are not used. In the other extreme, you set delta to be common. Then delta is just same as beta, like common effects. You are estimating things jointly across all groups. You don't really use the group information. So what we are doing is in the middle. So we have this group specific effect, like including random intercept, group specific intercept, and group specific slopes. But we're not estimating delta I individually. We're assuming they follow another distribution that's not specific to I. And then we just estimate the parameters in that distribution.
There's no common intercept, right?
The common intercept will be here. Beta 0 is the common intercept. So we start from this common intercept. We consider what is different from common intercept to group specific intercept. Their difference is the delta. So in this model, in the general form, in this model, the common intercept is already embedded into this beta. The first element of beta is the common intercept. And what are in the delta are group specific offsets. Like you may have an intercept offset that's group specific. You may have a slope offset that's group specific. So in this formulation, we will assume all the elements of delta I to have expectation 0 because they are the offsets. Does that make sense? Just like here, when we maybe go back to the random intercept model, just like here. Okay, so beta 0 is the common intercept. Delta I is just the zero mean random intercept difference. Yep. And what we're writing in the ZI is just to generalize this. So we can have not just the intercept difference, but we can also have the coefficient difference. Okay, so maybe I can just take another piece of paper to make him a little more concrete rather than abstract. If I just have one covariate, one intercept, so maybe I will just write Yij equals to beta 0 plus Xij beta plus gamma I or delta. Let me just use delta I. No, I just use gamma. Gamma I plus gamma 0 I. Okay, plus Xij gamma plus epsilon ij. Okay, if I write it this way, then I would just assume gamma 0I RIID 0 mean normal omega squared and gamma I RIID normal 0 mean, let's just say S squared. I'm just writing some notations. Epsilon ij IID 0 mean sigma squared. If I have that, then this model has a random intercept and a random slope. So I'm allowing each group to have its own intercept, its own slope. And these two are deviations from the common intercept and common slope, right? So then you can see that I can naturally put this into the form I just wrote. So if I do it this way, then Yi as Xi beta plus Zi delta plus epsilon I. If I write it this way, then this beta would just be beta 0 beta, and this delta would just be, delta I would just be gamma 0 I, gamma I, right? And then in this case, Xi is just 1 xi1 to xini. Yes. And zi is the same. In this case, zi is just equal to xi. Right? Yeah. So basically, you know that for the sake of identifiability, we always need to specify a baseline. If you remember that for the categorical predictor, we need a baseline. And then it's the offset from every level from the baseline, right? Okay, so coming back here, when we stack the groups, Y becomes big N by 1. So big N is the sum of Ni's across the groups. X, we stuck them x1 to xn. So this will be big N by P. Okay. And Z, that's the thing. Because, you know, we have delta I. We have delta I for group I. So therefore, each Zi is multiplied to its own delta I. Okay, so then we cannot just stack Zi as X, because for X, every column is multiplied to the same beta. So Xi multiplies to beta have the same columns, but that's not the case for Zi. So therefore, when we stack the Z, we need to do it in a block diagonal way. So we have Z1 to Zn in this way. So the number of rows is still big N, but the number of columns becomes N times R. So each ZI has R columns, and they are stacked column by column. So correspondingly, when each ZI is multiplied to its own delta I. So therefore, correspondingly, we need to stack delta as delta 1 to delta N. So this becomes an NR by 1 matrix. So then when you multiply Z by delta, you will have ZI delta 1, sorry, Z1 times delta 1, Zn times delta N. Does that make sense? Because if you stack Z in this way, you cannot afford different delta I's. Yeah. Yeah.
Maybe N is the total number
of
groups.
Observations.
What is small N with something?
Small n is a number of groups. So big N is the sum of I from 1 to N of Ni. That's the big N. So Ni is the number of observations in group I. We have a total number of small n groups. So like this N is not the same as this N. This N is the within group Ni, and N is number of groups. Yeah. But like I said, I feel like if you really want to learn the methods, especially I think in both regression and machine learning, I would say linear algebra is more important than calculus. You use linear algebra almost in every method, including neural network. If you want to talk about those gradients, like back propagation thing, it's basically vector calculus, but still it's vector. It's not scalar calculus. So you need to be familiar with linear algebra. I'm not sure whether this is something you were expecting when you enrolled in this class, but this class is not supposed to be just for our package or users. It's not like a tutorial class. So that's why we have to go through the linear algebra. But I feel like that may be the learning hurdle in this class for some students. But I just want to emphasize that I think linear algebra is very important, especially if you want to do method development, not just as a user. As a user, maybe understanding the R package is more important, right? The output, if you don't want to write your own code. But so that's why I think the learning objective is very important. Yeah. But still, I think being able to read it is also, if you check all the papers that mention the linear mixed model or the method papers, they use linear algebra. Especially, I think linear mixed model is most used in education, social science, and also genetics. I think genetic people talk about this a lot. The reason is that the individuals are the things we talk about, the subjects, and the individuals are genetically correlated. We cannot assume them to be independent. And the genetic architecture is actually built into the random effect. We're assuming that, so for example, what is in genetics is that you are interested in studying, okay, whether having one SNP in your DNA or one type of nucleotide in your DNA has some influence on your phenotype, like diabetes or height. That's the central question of genetics, how your DNA affects you. But we must consider that the effect can be dependent on your group, right? The ethnic group. Like your race will make you more susceptible to diabetes than other groups. So therefore, how do we build into group information? It's usually in the Z, in the random effects. So that will, this delta will actually allow us to say that following the common model, we allow some group-specific differences. And the group-specific differences are probably too many parameters to estimate. Therefore, we assume they follow some distribution, usually normal distribution, and then we just estimate the normal variance. So it's actually a very, how to say, practical strategy. I wouldn't say it's a scientifically true model. We can never say that for any statistical model. It's not based on some physical principles, or people say first principles. It's not a mechanism at all. It's just how we interpret our data. Yeah, so that's why essentially what happens in the linear mixed model is that we're doing variance decomposition, which we'll see very soon. So that is, we want to explain. So the reason we stack things together is that among this big N individuals, looking at their differences, all right, how much of the difference can be explained by the model X beta, the function we're interested in estimating? How much can be explained by the random effects that are group specific, the group differences? How much can explain that? And how much is remaining to be explained by random? So that's why it's about the variance decomposition. Okay, and why does it matter? If you don't have this random effects, if you just force yourself to fit a linear model, say yi equals xi beta plus epsilon I, if you just do that, then for the variance among the y's that cannot be explained by this xi beta part will be thrown into the variance of epsilon I. Then you will give yourself this impression, oh, the measurement error is very big. And assuming the measurement error is big, what's the consequence for inference, not just estimating beta hat alone? The effect on inference is that you would assume your estimate beta hat has a big variance, because the intuition is that the larger the measurement error, the less certain you have for your beta hat. Then you would think, oh, beta hat has a very big variance, and mathematically you can show that. Then I'm less able to use beta hat to tell me something about beta, like hypothesis test. But if you now think, okay, using the variance decomposition, a large proportion of the variance I cannot explain with xi beta can be explained by this random effect, can be explained by the between group difference. Then I think my random error has a less variance. Then I'm more confident with my beta hat. So my inference is more confident. Then that means I have better power for deciding whether beta is 0 or not. So that's why practically using this linear mixed model instead of linear model help you get better power when you want to do tests about beta. Even though it's the same beta, but we want to use the knowledge of groupings, the group structure, to help us do a better variance decomposition. So what is interesting about linear mixed model is that there's so many ways to justify or to say why we need it, right? You can start from this model-specific interpretation and say, oh, because we cannot for so many parameters, we just assume a random structure. That's a practical point of view. You can also say that, oh, I just believe that my groups are a random sample from all possible groups in the population. So in this case, I don't really care about these specific groups. I just assume that they follow some random structure themselves, so they are not equal. So that's another way to justify it. Yeah. All right, so any questions? I think understanding the model is more important than knowing how to do the estimation at this point. Yeah. All right, so that's the model stacking. So with the model stacking this way, then finally, we can stack the epsilon 1 to epsilon n. And again, this is big N by 1. So with all of them together, we get this big model. That's y equals x beta plus z delta plus epsilon. So that's what you will see in most research papers. They may directly write out this model. And again, dimensions n by 1, n by p, p by 1, n by nr, nr by 1, n by 1. Okay, so what we mean is that we have p fixed effects in beta to estimate. And we have how many? We have delta 1 to delta m. Each is R by 1. Each is R by 1. We have n of such random effect vectors. Okay, these are random effects of n groups. And they share the same R dimensions, but they're different, all right, because they are group specific. And typically, we would assume these ones to follow one R dimensional distribution. So typically, they are assumed to follow a normal distribution of R dimensions with 0 mean, that's R dimensional, and the omega covariance matrix, that's R by R. Okay, that's for the random effect. Finally, if we just want to be simple, we just can assume all the epsilon ij to be IID normal 0 sigma square. So I dropped that sigma I just to make sure it's the same sigma square. Otherwise, if I have sigma I squared, I have sigma 1 squared to sigma n squared to estimate. So n group specific random error variances. And these, like I said, if I don't have enough sample to estimate a group specific mean, group specific intercept, I may not have the sample size to estimate group specific sigma I squared. So then in that case, people can also assume sigma 1 squared to sigma n squared follow another distribution, right? So it's like another way to unify them into one prior. And people typically use the so-called inverse chi-square for that purpose. So inverse chi-square is kind of like a conjugate prior to Gaussian for the variance term. So this is all used in Bayesian. You can just add layer by layer to reduce the number of parameters you want to estimate. And conjugate prior is just set up for convenience. Basically, what it means is that using a conjugate prior, the posterior is in the same family as the prior. So that makes it easy. But we are not getting to that level of difficulty or challenge. Basically, we just say we have this. Okay, so then let me ask you, in such a model, what are the parameters we need to estimate? Beta, yes. Sorry? Exactly, beta, big omegas, yeah, sigma square. So these are the things. Let me circle them out. Okay, so you will estimate all three as a model output. Okay. Any questions? Okay, so one more thing we can say is that why do we say it's variance decomposition? Let me revisit that topic. I already said that verbally. So let me just get another piece of paper. Okay, let me just write this again. Y x beta z delta plus epsilon. Okay, so keep the dimension is crucial. Okay, all right. So with this, then what means if we do variance decomposition? That means if we're interested in decomposing the variance covariance matrix of Y, okay, because Y is a vector, then when we write variance of Y, it's basically an n by n covariance matrix, right? Then it's interesting that we can just use this model to do it because x beta is fixed. This is fixed, so we can live it out. So it becomes the variance covariance matrix of z delta plus epsilon, okay? And here, the independence between delta and epsilon is crucial, right? Because when we write out the variance of a sum, we need to make sure that there's covariance between the two terms, but they're independent. So therefore, because of this, random effects are independent of error terms. Then it becomes just the variance covariance matrix of Z delta plus the variance covariance matrix of epsilon, all right? And they're both n by n, that's the thing. And then because Z is just a covariate design matrix, it's not random itself. Therefore, we can write it as Z times the variance covariance matrix of delta times Z transpose. Okay, and Z by notation dimensions n by big N by small nr by big N. Okay, and this delta is nr dimensional, so it's nr by nr, it's covariance matrix. And this variance covariance matrix is just the epsilon at J. They're all independent. They all share the same covariance variance. So it's just sigma squared times identity matrix big N dimensional. All right. Okay. And remember, we said for the delta, what is that? What is the covariance matrix of that? Remember, how we stack things. Delta is just delta 1 to delta n, okay? And they are independent of each other, all right? So therefore, when we write this variance covariance matrix of delta, it actually becomes the variance covariance matrix of delta 1 to delta n. It's this block diagonal thing because they're independent of each other. All right, and they share the same covariance matrix omega, which is R by R. So it's basically this, omega, omega, n times diagonal. Okay, as this is diagonal, and we have Z stacked as Z1 to Zn, right? Block diagonal stacked. Remember this. This is we do the stacking. Okay, then what is Z times variance covariance delta? It's actually Z1 omega, Z1 transpose plus, right? Let me just write it this way. Okay, so therefore, just one more line. Z times the variance delta times Z transpose, it actually becomes just like this. Z1 omega Z1 transpose to Zn omega Zn transpose. That's it. All right. So therefore, you see that although I'm writing the stack form, but basically, you see, when I do the variance decomposition, if I just look at group I, for group I, the variance covariance matrix is Ni by Ni in that group. It's just Zi omega Zi transpose plus sigma square identity and Ni dimensional for each group. That's the variance covariance matrix. So you see that because this matrix is not diagonal, this is not diagonal matrix. So therefore, you see for Yij, Yik within the same group, they have some covariance explained by this term, okay? All right, so that's how we just have for the thing. But you see that even in this first random effect term, between the groups, because this is block diagonal, between the groups, we don't have any additional variance added by this term, okay? Mm-hmm. Mm-hmm. With omega, yes, yeah. Exactly. Okay, so this is the variance decomposition perspective. So you can see that we we can decompose the variance into the random effect part and the fixed effect part. All right, so then there's one more thing I hope to introduce, which is about the MLE. So we said that we need to estimate the parameters beta, omega, and sigma squared, right? So how do we do that? So basically, we use the likelihood. We write down the max likelihood, maximize it, and do the job. All right. So one thing we can do is basically we first throw everything in the random effect part into a general term. So we separate the fixed effect and random effect, making the random effect into one term. So let me just quickly say that if I want to do MLE of beta, omega, sigma squared. Okay, one way to do it is to write y as x beta plus epsilon star. Okay, so we just assume this epsilon star as the general random effect term. And we assume this epsilon star, which is big n by 1, to follow a big n-dimensional normal distribution. And we call its mean as 0, big n-dimensional, and we call the general covariance matrix as a big V with parameter theta. So this is n by n. So in this case, we use theta as a general notation for omega and sigma squared. So the variance parameters. Okay, so if we put it in this way, the only thing we care about is that it's still normal distribution. Okay, and then what we could do is that we could treat this just as a weighted least square problem. Okay, we just have the random error terms, not IID sigma square, but there's like a more different or more difficult covariance structure to take into account, just like in the weighted least square problem. But we can still do MLE. So when we do MLE, we just write down the likelihood of beta and theta, where theta is the general notation. Beta and theta, we write the likelihood. And because we use the Gaussian n-dimensional Gaussian distribution, let me just quickly say it. Then the log likelihood let's just say L beta theta would be proportional to 1 over the square root of the determinant of the V matrix exponential. This is the density of a multivariate Gaussian. Negative 1/2 y minus x beta transpose V theta inverse y minus x beta. Okay, that's the log likelihood in this model. So y still follows, basically, I'm just using the fact that y follows n-dimensional, big n-dimensional normal distribution with mean x beta, variance v theta. That's it. That's why the density looks like this. Okay, so for this, if we fix theta and just optimize beta, given theta, we can easily see that the beta hat MLE, given this theta, so it becomes a function of theta, it's just the formula we are familiar with, x transpose V theta inverse x transpose V theta inverse y. Okay, the weighted least square formula. And then how do we find the estimator of theta? We put this estimator of beta into it because now it's a function of theta. So we're only left with theta. So therefore, we would have this is called the profile likelihood, which means that we already take the MLE of beta given theta and put that back. So it becomes, we call this LP stands for profile of theta, is written just as the likelihood with beta plugged in as beta had MLE at theta and theta. Okay, that's the profile likelihood. And then we maximize this one to find the theta value. Okay. So it's still the MLE. It's just that we maximize the likelihood in 2 steps. Okay. So another way to do it is to do the so-called marginal likelihood. You would have both when you want to estimate theta. So marginal likelihood is written as L big M for marginal theta. So what it does is that you take the integral of the joint likelihood beta theta, you integrate out beta. Okay, if you do that, you will get a likelihood for theta, marginal likelihood for theta alone. So the difference is that one, it plugs in the beta had MLE. So this is like the real MLE for beta and theta jointly. And this is the marginal likelihood where you integrate out beta, which means that you are considering all possible values of beta, not just a particular value of beta. Okay, and then because it's like normal density, so you can possibly do this. You can integrate out beta, and then you can have a form which is, how to say that, which is actually proportional to, I wouldn't say proportional, but basically you will have a form that's not the same as the profile likelihood. So let me just quickly give you the result and wrap up. So let's say we have the log marginal likelihood and log profile likelihood, and their relationship is that log marginal likelihood of theta can be shown as the marginal profile likelihood of theta minus, sorry, log profile likelihood of theta minus -2 log of this determinant, log of x transpose v theta inverse x. So you have this additional term in the marginal likelihood, log marginal likelihood, but not in the profile log likelihood, log profile likelihood. So therefore, if you maximize this to find theta hat, it's not identical to the theta hat by maximizing this. All right, so therefore, there are 2 terms used in this literature of linear mixed model. So we call this theta hat as REML. So it is called, what is it? It's called a restricted maximum likelihood. That's just the R max of LM theta. All right, while you have the theta hat ML, which is R max LP theta. Okay, and if you think about this problem from, like, if you think about this as your objective function to maximize in just like a simple objective setting, or if you think about negative of this as your loss function to minimize, then essentially, if you add a negative sign here, this becomes positive sign, this can be considered as a penalty term in your optimization. Okay, so in general, people found that with this penalty term, the restricted ML theta hat has a smaller variance. It's more stable, right? But it may be biased. So therefore, basically, you can have 2 versions of estimators. And in the R function, the LME4 function for doing linear mixed model. So in R, I think package is called LME4 function. LME4 package, I should say. So in that package, you actually have both options available. So have 2 estimators to choose from. And whatever one you use, the beta hat will be correspondingly estimated. You just place that theta hat into this form, and then you get the beta hat as your coefficient estimates, the parameters of the interest. Okay, so that's basically what I want to say. And let me see if I made a mistake or something. Interestingly, sorry, I think I made a mistake. I should clarify. Actually, this REML, this one is unbiased instead of biased, while the ML one, this one is biased. But it seems to be a little counterintuitive here. Okay, so they have this bias, they basically lie on a different position in this bias variance trade-off thing. Yeah. But hopefully if we come back on next Monday, I will try to just say a few more words to wrap up this part. Yeah, basically, I think in practice, what we do the most is to use the linear mixed model to do some variance component test. So basically, the covariate of your interest can be formulated either as a fixed effect or as a fixed effect covariate or as a random effect covariate, depending on whether you are just interested in whether its effect is zero or not, or you are really interested in getting the effect size, like the beta. Because scrolling back to the model right here, you see that if you want to estimate, or if you want to put your covariance of interest into X, then you want to get a beta hat values. That's your estimated effect size. But if you put your interested covariance into Z, you won't actually get a theta values. You're just trying to see whether this part theta contributes a component in the variance, whether its variance component is zero or not. Essentially, that's actually for the same purpose of testing whether it has effect or not, that you save your effort for not getting the effect size values instead of you just do the test. Basically, you have a less burden in your parameter estimation. Yeah. Right. So I think in genetics, people typically put the DNA information in the Z, right? Because there are many positions you want to look at, and you don't care about their individual effects. You just want to know whether collectively they make a difference or not. So that's why you do a variance component test, by testing whether, essentially, you are testing whether this term, you are basically testing whether this term contributes anything. Okay. Okay, so maybe we'll stop here and then we will come back on Monday. Yeah, on Zoom. If you have any questions, you can stay here.